Our next talk will be a review of the Allotrope repository, just an update from our friends at Benchling. Nathan is going to be giving a presentation to let us know about the latest in the shared repository, and then I will add just a few comments on the end, just giving you one example of how we're using it for another project we didn't talk about yet at Merck.
So my name is Nate Stender. I am a software engineer at Benchling that heads up the Allotropy project. So I say Allotropy. Some people do say Allotrope. This was complicated recently when we learned that the actual pronunciation of that scientific term is Allotropy, which really threw me for a loop. So I continue to say Allotropy for no good reason, just what I started saying. So yeah, you've heard a little bit about Allotropy. I'm going to give a deep dive into the library itself, what it looks like to contribute a connector, and the tools that we've developed to make that as easy as possible. My goal is to convince you that it's really easy to contribute a connector and that you should do it, and it's worth your time. Cool. So let's go into that. So Allotropy is a Python library for converting raw instrument data to ASM. It's live on PyPI right now. You can check it out and use it in a script for yourself right now. Essentially, it has one interface. We take in a raw data file as a bytes or file object, and we spit out ASM JSON. So the middle part of this data flow diagram is what I'm going to dive into, what actually is happening in Allotropy. But real quick, so we have 8 schemas currently supported. We also are adding binding affinity soon. We have a draft PR up to add our first binding affinity converter. We also have a liquid chromatography ASM in the repo. We don't have any parsers right now because, as has been mentioned a couple times, the liquid chromatography devices in particular don't like spitting out files. They like more complicated connections. So we have a couple API adapters that talk to liquid chromatography, and we use the schema in Allotropy to do validation for our API adapters, but we don't have any file connectors right now. We're also working on one of those at this time. We have 34 parsers. So a parser here is a specific library to talk to a specific piece of instrument, or really read from the output of a specific instrument software. And we specify software here because some instrument softwares run on several different instruments. And so those 34 parsers get us to support for over 100 instruments right now. So yeah, looking at what it actually looks like to add a parser to the Allotropy library. So this kind of shows an exploded view of that middle graph. And Allotropy is not just a code repo for hosting ad hoc solutions for converting various different softwares to ASM. We have a code architecture that we hope makes it easy to contribute an adapter, easy to understand what's going on, and yeah. So when you want to add a new parser for a new instrument, you're going to add 2 or 3 different things depending on the scenario. First, you've got a reader. The reader class is responsible for reading in the raw data from the instrument and putting it into like an accessible format. Most of the time, this is pandas data frames. You might have one data set. You might have a file that has 3 or 4 different data sets. The parsers, or the reader, is just reading this in, getting into those data frames to be used by the next step. And really importantly here, we have a lot of pre-built libraries for common use cases. If you're just reading in a CSV or an Excel, you don't have to write anything new. You can just use the util we already have. For more complicated text files, we have some tools that let you scrape through the different sections of the file based on some simple rejexes to get that data out. The second step is the ontology mapping, which we call the structuring step. So there's a file in your parser folder called structure. This takes in that reader or the data set that's produced by the reader, depending on the scenario, and maps that into the actual ASM ontology. So if you have a data set, for example, this is basically saying which columns in that data set correspond to which ASM fields. And if you have a more complicated structure, sometimes it's first organizing it into like if you have data sets that are cross-referencing each other, organizing those data sets into groupings, and then pulling from multiple different sources to compose a single measurement document, for example. And then the third thing that you may or may not have to add is a schema mapper. So a schema mapper is a library that we have that assists in populating the full ASM JSON. You only have one schema mapper per ASM, so if you're writing for one of the instrument categories that we already support, there's no need to write this, it's already done for you. And this makes it easier to populate that nested document format. It also decouples from the schema versioning, so it makes upgrading to the next schema very easy. Usually you just have to make a couple tweaks and you don't have to change anything in any of the parsers and everything just works. So yeah. In addition to this code structure, we also have a suite of tools to make it as easy as possible to add a connector. So I'm going to go through these tools individually, so feel free to raise your hand on any one of them. They cover kind of different areas, or ask at the end, either way. So first off, we have boilerplate code automation. So basically, that structure that we ask you to format, we have a script that automatically makes a skeleton for you, so you don't need to worry about touching the code in a lot of different places. We have file parsing libraries that, like I mentioned, help read in common use cases. We have Python models for the ASM schemas. So basically, we translate the schema into Python classes that you then use to fill out the ASM. We have the schema mapper that I mentioned, and we have test case automation, which makes it very easy to add new test cases when you have sample data, and lets you start doing test-driven development right away. So another look at this graph with these tools, you can see kind of where each tool helps simplify this process. And you squint your eyes, you can kind of see that basically the goal here is to chip away at all of the repeatable parts on either side of the ontology mapping, and make it so that you have to do as little work as possible and just focus on the ontology mapping when you're writing a new parser. Yeah, so going through these tools a little bit deeper. So first, the boilerplate code generation. So when you check out the Allotropy repo, get things set up, there's a single script that you run to start writing a new parser. You can see on the left here, this generates all the files that we expect that you'll probably be adding. Sometimes for more complicated parser implementations, there might be a few more files that you add, but this is generally what their parser folder is going to look like. And then on the right here, you can see this is the full contents of the parser itself. And a lot of times you don't even have to edit this file because the parser is just kind of the glue that moves the data from one library to the next. It takes in the raw data, calls the reader, then passes that reader down to the structure. And then by specifying the mapper in the class, it says what mapper is going to be used. And the Allotropy library automatically takes the output from the parser and does the schema mapping. So yeah, Allotropy, I think one of the most important parts is we have a suite of libraries for reading in various input files. Anyone who's worked with instrument outputs knows that a lot of the file outputs are just a random text file that's structured in whatever format the person who wrote it thought first. The example here is Softmax Pro, which is organized into sections, but there's no particular order to them, I don't think. You can have any combination of results and groups. So we have a lines reader that reads in that file. You specify a regex that says what section you're looking for, and it iterates through and gets you each of those sections, and then you define code to read that in. In this case, usually reading those into data sets. Yeah, we use that for a few of the different parsers for text files. And every time we add a new one, we end up adding a couple new features that we see that make it easier for everyone. The other thing that's really widely used are a utility around pandas. So basically, this lets you iterate through the rows of a data set and provides you from each row with a wrapper around that pandas series that gives you a dict-like accessor, dictionary-like accessor, that lets you do presence checking, type checking. You can see there that for each of those values, we're specifying the data type we expect. And so if you expect something using the index operator, or you say that you expect a float and we're not able to turn it into a float, it returns a helpful error message to either the customer or you while you're developing. Also recently added to this tool is the ability to detect if you're not reading in any of the data in that row. And we're able to like surface warnings to you while you're developing. And also, if there are some columns that just don't fit in the ASM ontology mapping right now, you can automatically dump all that data to the custom info document to ensure that you're not missing any of the instrument data. So basically, as long as you can get it into a data frame, we can make sure that you're capturing all of the data without any additional work. We also have an XML reader. It's similar to the Pandas reader. Could use a little more maturity there, but we're working on it. Okay, then in order to actually do the ASM population, populating the ASM, what our library does is we have a script that turns the ASM schema into a set of Python data classes. If anyone's familiar with Python data classes, you can specify them with required fields and optional fields, so these directly reflect what the ASM schema has. What this gets you is, instead of versus manually filling out the ASM JSON, is that you can populate them in Python with tab completion, and if you fail to populate something or use the wrong type, you get type checking when you're running the JSON tests. Yeah, and these are not manually generated. We have a script that lets you download any ASM schema from the Perl repository, and another script that generates all of the Python classes for you automatically. So usually adding a new schema is 2 lines of command line code, unless there's a bug in the schema generation, in which case you ping me and I fix it, and then it just works. So yeah, then the intermediary step for populating that Python class. So like having the Python classes is very useful. You can see on the right here, this is populating the measurement document for a plate reader, using that data. But there's still a bit of a challenge in that it's heavily nested, and there's a lot of boilerplate code in here. So again, this is like a challenge with this structured data. It's very useful to have the ASM output and have it structured with context of what each thing is. But when you're actually just doing the ontology mapping, that's not that important to you, and it really just makes it take a little longer to like fill out this code. So on the left side, we have each schema mapper defines a flattened ontology mapping, where basically all of these things are grouped under a single ASM. We sacrifice a bit of the safety checking when you're actually writing the code, but of course this gets tested when it gets populated by the schema mapper. And this just makes it a little easier when you're writing the parser to fill out just this measurement document on the left, and then the schema mapper takes that and fills out the full ASM with all of the structuring. Yeah, and as I mentioned, this gets you away from having to worry about version upgrading, and because you only have to write them once per schema, or once per schema class, it's not like a huge amount of lift to do this. Finally, we have tools in our testing library that allow you to do no-code test addition. So basically, every parser, when you run that script to generate the structure, creates a folder for that parser in the testing section, and it creates a test data folder. Any file that you drop into the test data folder automatically gets picked up and run as a test case for that parser. And the first time that you drop it in, it detects that the expected output is missing and generates that automatically. So when you first start writing a parser and you have some sample data, you can just drop those files in and start running your parser against it without any additional unit tests. This just makes it really easy to start doing test-driven development immediately. The testing case, like that general test case, validates all the output against the ASM schema to make sure we're producing valid ASM. Of course, we still encourage you, after you're done developing, to write specific unit tests for any special logic you have in the structure. But a lot of times when you're just reading in a single data set, for example, there's not really that much that you have to add. The libraries are already tested. Oh yeah, and then when you're iterating on this, say you want to go in and add a new field, obviously the ASM that you produce is going to be different. There are a suite of like command line flags built into our testing util, so -- overwrite lets you purposely overwrite the file when you know that it's not going to work anymore. It'll update the test file, and then you just have to inspect the difference to make sure that it looks good still. All this comes together to mean that for a simple parser, and I do clarify simple, I'm talking like, again, a lot of these instrument outputs where it's just putting out a data set that you just need to map to ASM. You can write the entire parser in about 100 lines of code. This is the entire non-boilerplate code for one of our parsers. And even this could be reduced. I mean, the reader is basically just calling in the CSV library, doing a little bit of cleanup, and then we do the ontology mapping in the structure class. Bigger parsers, I looked, the biggest parser we have is about 1,300 lines of code. This is for one where we support multi-sheet Excel with results, data cubes, all that stuff. Still, it's not too hard to follow, I don't think. Yeah, so if I've convinced you at all, there are a lot of ways to help us out here. Obviously, you can contribute a connector or features. We just had our first external contribution, which was adding support for a whole new format in one of our parsers, but no one has contributed a brand new connector yet. So you could still be the first external contributor to add a new connector to the library. I'm sure Benchling would, I don't know, say thanks. You can give us test data. This has been a common theme that I've heard, when trying to develop the ASM schemas as well. One of the hardest things of this is getting examples of the instrument outputs from certain vendors, or just getting like different examples for the ones we already have. If you have test files that you can share and you would like to see supported in Allotropy, you can open a GitHub issue against the repo and upload them. Obviously, at Benchling, what we're working on is determined by customer needs, but it is an open source repo, and sometimes I get bored on Saturdays, so we will get to it eventually. Testing connectors, if you have one of the instruments that we support and you want to produce ASM, like I said, you can, even if you're not associated with Benchling, you can write a script and call this. And again, another common theme is that all these instruments output in several different formats, sometimes for no reason at all. I know for a fact we have some test cases where there are 2 or 3 different files that all produce the exact same ASM because there are commas or there aren't commas, or et cetera, et cetera. So if you run a test and it doesn't work for you, again, you can file a ticket, provide us with that test file, and we will definitely add support to existing connectors if you file a ticket. You can raise issues for bugs that you notice, and you can spread the word. Tell your coworkers about Allotropy, give a star on the repo. That's my version of like, share, and subscribe. The more stars we get, I don't actually know what it does in GitHub, but it does look nice when there's lots of stars. Yeah, that's what I've got.
Yeah. So I could either be making an announcement of the first contribution, but I'm not. I'm going to talk about uses. So at Merck, and another use case that we hadn't spoken about. Sorry?
Your slides there.
They're up.
Oh, they're on there. Okay.
Yeah, we're good. Thanks. So another use case related to some of the other ones before, again, same general theme. Merck is making a lot of investments in modernizing our bioanalytical capabilities for vaccine bioanalysis, and Essentially, if you look at this slide going from left to right, it's going from, and we picked the most depressing pictures I could possibly put, but this depressing, manual sample management, assay execution, reporting, data reporting kind of workflow that honestly I entered Merck a few decades ago doing things like this, to move towards the vision for some of these new bioanalytical facilities of really end-to-end automation, sample management, lots of robotics, maybe not lights out, but sort of like here where it could be in this room, I think, in a few minutes if we don't put the lights on. Not too many lights, and really end-to-end integrated sample management. Which computer? This one? Okay, yeah, great. So what's the punchline of this little add-in? So this is a live reference customer testimonial of using the Allotrope or Allotrope repository for this solution. There are on the order of probably 50 different model of instrument converters that are going to be necessary. Have them listed here. A good percentage of them are already available. A few others, most of the rest, I think, will be available and in production either first or second quarter next year. Let's call it first half of next year to really power this facility. So this is an example of, again, when you're making these sorts of decisions and these sort of things are available in a repository like this, it makes it certainly as an individual customer pretty easy to make a decision to move forward. So again, applaud what you're doing and ask others to please consider contributing to this repository. A call certainly to my friends who make vendors who make software. Just imagine how quickly we could populate this repository if you use these tools and you just took care of your own software. We could populate this repository pretty quickly and then get on to the next phase of Allotrope, which is talking about what the cool things we're doing with the data. So please consider that. Okay, with that, don't thank me. Thank Nathan